So here we're going to review some of the key ideas about potential energy curves. First, some general concepts. We have two functions. One is the potential energy, and the other is the force function. They're related because the work done by a force is equal to the loss in potential energy, which is to say when a force does work, the associated potential energy has to go down. And the work is equal simply to the integral of f dot dx, which makes the potential energy essentially the antiderivative of the force, which suggests that the force is the antiderivative of the potential energy. And again, we need the minus sign here to keep our sign conventions consistent. Oops, I did mean the derivative, not antiderivative. Some key terms here are the distinction between conservative and non-conservative forces. These relationships up here only work for conservative forces, which is to say forces for which this integration right here depends only on the limits, not the path taken to get from the start to the end. For some forces, the value of this integral does depend on how you get from the start to the end. Those would be considered non-conservative forces, which means they have no unique potential energy function, and therefore they are called non-conservative forces. Friction is an example of a non-conservative force. Another point is equilibrium. Equilibrium is where the derivative of the potential goes to zero, because at that point the force is zero. So that is a point where an object, if it's there, will stay at rest. However, we will distinguish between two types of equilibrium, stable and unstable, which shown right here is a stable equilibrium, so that if the object is displaced a little bit to the left, the force, it will be a repulsive force, because right here the slope is negative, so the force is positive, and the object will be pushed back to equilibrium. If you displace it so it's a little bit further away, then the force will be pulling it backwards. It'll be an attractive force because the slope here is positive, the force is negative. The force will push it back to equilibrium. So that here, if you do displace it away from equilibrium, it'll tend to return back to it. An unstable equilibrium is the opposite. That would be sitting on the top of a hill, where if you displace it a little bit to one way or the other, the force will push it further away, and you will not return to equilibrium. Stable equilibriums have what we call restoring forces. That's what we're seeing right here, so that the force always brings you back to equilibrium. Turning points are points where the velocity goes to zero and the force effectively is not zero, so it pushes it away from that point. That's a point at which the objects change their direction of motion. Not always stated, but often what we're thinking of when we have these potential energy functions is, for an example, something like a diatomic molecule, where the x is actually the distance in between the two atoms. And that's one of the typical examples of a potential energy curve. So now we can take a specific example. So let's let u of x equal 2 divided by x to the 6th minus 6 divided by x cubed. What I want you to do is first just take and plot u of x. So pull out your calculator and plot that function and see what it looks like. This is what you should have gotten, namely something that does indeed have this little dip right here, so there would be a point of stable equilibrium. This is a typical potential energy curve that you would see for a diatomic molecule. Then I want you to find the force function by actually taking the derivative and remembering the minus sign. So take a moment, find the derivative of the potential function, and this is what you should get. The force is minus du dx, which is 12 divided by x to the 7th minus 18 divided by x to the 4th. Now again, I want you to plot that by plotting it in your calculator. And this is what you should end up with. Namely, it looks kind of similar to the potential curve, but it is definitely different. Because this point right here where the f is 0, that was the minimum before. This point right here is where the force is a maximum. That's where the slope was a maximum. Or, if you will, where we have an inflection point. The force goes to 0 because the potential energy curve also flattened out at the end. So the force does go to 0. So that's what the force function would look like. Now we're going to take a specific example of this system. So we're going to have, for an example, a diatomic molecule where the total energy of the molecule will be minus 3 joules. And we want to describe the resulting motion and find any turning points. So here I've plotted the potential energy curve. And this orange line right here is the total energy. The blue is the potential curve. So our first point is to find this point of stable equilibrium down here. So there we basically set the derivative of this equal to 0, solve the resulting equation, and this is what we get, about minus 0.87 meters, which is right where that stable equilibrium point right here is. Then we want to find the turning points. The turning points are where these two lines cross, right here and right here. So we set this function right here equal to minus 3 and solve it, and we get 2 points. We get these two turning points, one at about 0.75 and the other a little bit greater than 1.16. Those are the two so-called turning points. And again, you can solve those using your graphing calculator and solve them numerically. You don't have to actually plug all these in. Let x be the distance between two atoms, and here are two atoms. X is the distance in between them. The kinetic energy is equal to the difference between the total energy and the potential energy, and that's got to be positive because kinetic energy has to be positive. That means the only place the two atoms can be is where the potential energy is less than the total energy. So it can only be in this region right here where the blue curve is underneath the total energy. It cannot be over here. You can't, with that much energy, they can't be pushed any closer than this or any further out than here, because then the kinetic energy would have to be negative, and that can't happen. So at x1 and x2, the two turning points, the total energy is equal to the potential energy, or the kinetic energy is 0, and the velocity is 0. At this point right here, we have the slope is negative, so the force is positive. So right here, it is at a velocity of 0, and the force is pushing it back towards the stable equilibrium. So when the molecules get this far apart, they'll tend to basically stretch and move further away. At x2 out here, we have a positive slope and a negative force, so they get pushed back in. So the two atoms will oscillate back and forth, so the distance between them will get no closer than 0.75 and no larger than 1.16. So these two atoms will just oscillate, getting closer and farther apart. That would therefore be describing the motion. The two atoms will oscillate apart, with the distance being no closer than 0.75 and no further than 1.16.